Let's talk about the right and relevant skills that we need to learn and practice before taking our FE exam. So what the heck are these skills? What am I talking about? So we know, first of all, I want to say that the FE exam is changing. So year after year, this exam is changing and they're actually testing the concepts more. So they're testing not just how to apply an equation, not just how to put in numbers and get like a final output or a final answer. They're also testing our conceptual understanding. And one skill that we will learn today is looking at an equation and breaking it down. Let's say you break it down into one variable. So let's say we call that the independent variable. We isolate that with respect to that equal sign. Then we're going to see that variable is going to depend on other variables in the equation. So what happens, let's say, when we increase the flow rate? What's going to happen to the hydraulic gradient? Let's say that's the independent variable. Or let's say what happens when we change the K value, the hydraulic conductivity? If that increases, what's going to happen to the hydraulic gradient? So you see here what we're doing. We're looking at a relationship between variables in the equation. And this week, we're going to learn just that. And if you're looking for FE exam tips, ideas, motivation, make sure to sign up to my newsletter below. So I'll be sending you weekly emails talking about FE exam tips, talking about study techniques, learning method. These are scientifically proven learning methods that are going to just make your FE exam prep a lot more effective. So check out the link in the below, sign up for the newsletter, and you'll be getting these weekly emails. Okay, this is a good one. So let's read that problem statement first and note what we're given, and most importantly, know what we want to find. So let's read that problem statement. We're told, select the correct graph. So we want to select the graph, select the correct graph, showing the change in horizontal hydraulic gradient, dH over dx. So we have this hydraulic gradient in play here. So change in the horizontal hydraulic gradient along the length of the apparatus going from left to right. So let's look at some keywords. So we want to select a graph. So that's what we want to do at the end, select that graph. So this is what we want to find. But we want to find a particular type of graph that shows the change in hydraulic gradient, which is like the gradient, or we call that the I value, which we'll get into. So the change in that gradient along the length of the apparatus, and that apparatus is just this thing that we're given. So that is our apparatus, so-called apparatus. And we know it's going to go from left to right. So be careful here. The flow is from left to right. It's not this way. This will be important as we will proceed and discuss, but it's going to go this way, from left to right. And we know here this is the apparatus, and that apparatus, you can think of it like a confined or an aquifer. Let's say an unconfined aquifer. We know aquifers are underground, and in this case we're given like different sections of these sandy soils. We know that section A is like a sand, just sand. Section B is actually the same. It's a sand material, same material here, but section B changes in area. And then section C is a fine sand. So fine sand for section C, different than these types of materials. So then we have, in this case, 4 options, multiple choice, and we want to select the graph that shows the change in hydraulic gradient, as we see here, with respect to the length going from left to right, going from left to right. How does the I value, the hydraulic gradient, change going from left to right? That's what we need to answer. So now, what would you do? So what would you do in this case? So first of all, you have to have like a basic understanding of the governing equation for groundwater flow. What is that governing equation? Darcy's law. Darcy's law. And we know that dH over dx in the FE handbook, in the PDF, is actually used in Darcy's law. So it's going to be in that equation. Now let's write that Darcy law equation, because we're going to actually use this to answer this question. So what I'm going to do is write this down and get it from the FE handbook. I'm using the FE handbook, so I want you to pause the video and get the equation for Darcy's law. So let's write that, Darcy's law. And I'm using the form in the water resources section in the FE handbook. So Q is the discharge, and that equals to negative. So that negative here, let's break this down. It's going to be just saying that water goes from high head to low head. Because if you think about it, high head is going to be where we start. Imagine like high head being an elevation of 100 feet, whatever it may be. Low head, imagine it being an elevation of 50. And let's say this is H2, this is H1. And you can imagine piezometers and all of that. But in this case, let's just keep it simple like this. High head, low head. What you do, the change, the delta H, basically our DH, you take H2 minus H1. When you do 50 minus 100, you're going to get negative 50. So you put negative 50 times a negative, that negative in the equation, which gets you a positive Q value. So it's just there to account that water is always going to travel from high head to low head, high elevation to low elevation. So always know that. So that's going to be why that negative is there, but it's not that important for this question. We'll probably take it out as we continue. So then we know the K value is the hydraulic conductivity. And we know the K value is like measures how easy water can flow through a soil material. So we know the hydraulic conductivity. If I had to ask you for gravel versus clay, which one has a higher hydraulic conductivity? It will be gravel, right? Gravel has a higher hydraulic conductivity because water can travel more easily. So if we measure the travel of water, it's going to travel more easily than when we compare it to clay. Clay is very dense. It has a lot of small particles, so water will not travel that easily. So once again, for gravel, the hydraulic conductivity is a lot higher than that when we compare it to clay. So that's what the hydraulic conductivity measures. So then we can continue. The A value is going to be just a cross section. For aquifers, we're usually looking at the thickness times the width, but in this case, we're keeping it simple and looking at the cross-sectional area of a circle. But that is not going to be that important for this question. Then we have the very important dH over dx per FE handbook. So now, dH is the change in head. You can think of this as dH, basically the difference between these, H2 minus H1. And dx is the length along the flow direction. Note that dx doesn't have to be strictly a horizontal x distance. It can be inclined. So just remember that. A better way other books use is dl, but dx is just the length of that flow direction. So then we have all of this, but the main term that I want to focus on here, that we should focus on, is this, which we call the I value. So just know, I'll write down on the side, the I value is the hydraulic gradient, dH over dx, which is the same thing as the change in head over the change in length, or we can say the change in x, the change in distance. But remember, it's along the length of the travel path. It can be inclined. So this is going to be the hydraulic gradient. So then we know that is the case, and what we're going to do next is going to be isolate this term. So I want to do this, and we want to do this on purpose because we're going to relate that I value to certain parameters or variables that are involved in what we're given. Specifically, those variables will be the area and K. Q is not that important because we know the Q value is just going to be the same all throughout. But what is important is going to be the K value, most importantly, and the A value. And remember, we're looking everything with respect to the I value. So what we're going to do is isolate I using this equation. So what I can do next is denote I like this. We can say Q equals, I'm going to take out the negative in this case. It's not that important. It doesn't become important. And we discussed why we have that negative. Then we know we can say Q equals KAI, or you can write Q equals KIA. Remember, from the rational method, you can relate it to that to help you memorize this equation instead of using the handbook. You can say Q equals CIA. CIA from the rational method. But now let's use Q equals KIA per the Darcy's law. So that's one way I remember it. So we can say Q equals K. K is the hydraulic conductivity. We can say I, then we do A. So now we have this equation. Let's isolate I, because I know that's what I want to focus on in this problem, on that y-axis. So I is going to equal to the Q value and we take that divided by Ka. So I believe you would agree this is true, right? So now we isolated I, the hydraulic gradient. So now based on this, we can arrive at some conclusions. Now, the conclusions are as follows. We will say, okay, the first one is, we will say that the I value, if you look at that equation, the hydraulic gradient is going to be proportional, directly proportional to the flow rate. All this means is if you increase I, Q will increase. Or another way, the better way to think about this, if you increase Q, the I value will go up. Now, another one that we can get from this is going to be the I value. So this sign just looks at the proportion, is going to be inversely proportional to the K value, the hydraulic conductivity. So inversely, the way we show that is 1 over K. So what does this mean? So let's say you increase K. Let's say this goes up. What happens to I? It's inversely proportional. It's going to go down. Or think about it this way. What if the K value goes down? What happens to I, the hydraulic gradient? It's going to go up. So that's what we mean by inversely proportional. And we got it by looking at that equation. And the last one we can get, you probably got this. It's going to be the I value is going to be inversely proportional to the area. Same thing with this. If we increase A, the I value is going to go down. And if we decrease the A, the I value is going to go up. Inversely proportional. And these are actually the big relationships that we can arrive at that look at that hydraulic gradient as like the independent variable, and it's going to depend, let's say, on Q, the K, or the A value. And we're going to use that to answer this question. Most importantly, we're going to use this term. This will help us immediately get that right answer, the one with the hydraulic conductivity. So now let's go above. Based on this, we will say, okay, now we have to look at this and think of the K value once again, the K value. If I had to ask you which section, section A, section B, or section C has the highest hydraulic conductivity, which one has the highest hydraulic conductivity? So remember, hydraulic conductivity measures how easy water will flow through a material. And if you had to look at this, well, if you compare this, these are the same, right? So we know that the sand here, both of these will have the same K value, the hydraulic conductivity. But this one will be different. Which one is easier for water to travel through? We can conclude that the sand, in this case, will have a higher hydraulic conductivity than the fine sand. Because, remember, hydraulic conductivity, how easy water will flow. It's a measure of how easy water will flow through the soil or material. In this one, you can imagine that water will flow easier through the sand because look at it has like more space to go through. And we know hydraulic conductivity is highly dependent on that pore space as well. So this one's going to be easier. And note, this sand is the same as this sand. So they're both the same. They're going to have the same K value. But this one, if you imagine, the water is going to hit a lot of these particles. So we have more losses, more energy losses. That we know the water is not going to travel easily through the fine sand. So it will have a lower K value, a lower hydraulic conductivity. And the way we can denote this is for the sand here, both of these are the same. We can say it's going to be a big K. I'm going to denote it by a big K. And it's the same big K here. They're the same for the same hydraulic conductivity for that sand, section A and section B. But now for section C here, we know it's going to be a little K, a little hydraulic conductivity. It's going to be small. It's not going to be that big. So now, based on that, we can use this relationship. Let's just use this one. Let's rely on that. And let me write that here for us. We will say that the I is going to be inversely proportional to 1 over the hydraulic conductivity. So now, if you had to look at this, comparing section C, section B, and section A, which one would like essentially change the I the most? Change the I the most with respect to changing the slope. Remember that the I value is like the slope of the hydraulic gradient. I would say that fine sand, because both of these are the same. They're not going to do much. They're the same. The one that has like a big difference is that fine sand. That fine sand has a lower K. It's going to do something. So now what we will say, okay, if we have a very small k here, this goes down, what happens to the I value? The I value is going to go up. It's an inverse proportional relationship. So if the I value goes up, that means the slope is going to get steeper. It gets steeper. When the hydraulic gradient goes up, you have a steeper slope. If it goes down, you have a flatter slope. Steeper, when it increases, it's going to be flatter when it decreases. So we know in this case that this section, compared to what we have here, compared to like section B and section A, this section should absolutely have a steeper slope with respect to that hydraulic gradient because of this inversely proportional relationship. So we will say, okay, we can actually eliminate two answer choices. Which ones would you eliminate? It's going to be B and D. B and D, because notice at the very end, section C is where we want to focus on, and that's going to be the section where we have a steeper slope. And the steeper slope would be here compared to the other sections, and it would be here at the very end for section C. Now we eliminated two answer choices. We have a 50-50 chance. Is it A or is it C? So now we can actually answer this right now based on the direction of flow. So just remember this, that the slope of that gradient is always going to decrease in the direction of flow. So where's the flow going? The flow is going from left to right. We're going this way. We're not going this way. We're going this way, left to right, where the Q comes in. So that means is the slope of that gradient, or think of it as the slope of the water table, is going to decrease in that direction, left to right. So which one would you pick in this case? Is it A or is it C? Take out A, because notice how it increases in left to right. That is not true. We said the slope is always going to decrease in that direction. In this case, left to right. So it has to be C. The answer has to be C in this one. And it would be A if this wasn't going from left to right. If it was going from right to left, it would actually be A. Steep slope for this, then it gets flatter, then it gets a little steep. And we can actually prove that this part is like a little, so here you can imagine this being a little flatter. This one is going to be the middle based on that area. Notice how this one has a big A, this one has like a smaller A. So if that has a big A for that, like a bigger A, based on this relationship, if this goes up, what happens to this? It's going to go down. It's an inverse relationship. So the A, the big A, we have a big A, it's going to go up. The I value is going to go down. So as the I value goes down, we said what happens? It gets flatter. It's going to get a little flatter. It goes down. It decreases. The hydraulic gradient goes down. The slope is going to get flatter. So for the middle section, the big A in this case, we will have something a little flatter, in this case, as we show here, which is going to be, most importantly, this one, the correct answer. This one's going to be flatter when compared to what we have here. This one's a little steeper, just a little bit, because the area in that one is actually going to be smaller. It's a little A compared to, let's say, section B. And that would be that. So this portion is like this portion. But at the end, we know the answer in this case must be C for this problem.